Welcome to this recitation. Today we're going to be talking about computing magnetic fields. To recap the recitation, which happened a couple of weeks ago, so I know that many of you might have forgotten a lot of what was talked about, magnetic forces obey the Lorentz force law, which is given here. The force is equal to the charge times the cross product of the velocity and the magnetic field. We then discussed the simplest magnetic objects, which are magnetic dipoles, modeled by loops with a current. As you can see in the diagram here, you have a loop with a current running through it. It has an area A, and the vector describing the magnetic dipole moment is mu. Mu is equal to the current times the area, and you can figure out the direction of mu from the right-hand rule. The resulting magnetic field is equal to mu naught over 2 pi times n times a over z cubed. I put in n times I times a, where n is the number of loops that go on here, I is the current, and a is the area, so this is related to the magnetic dipole moment. Mu naught is a fundamental constant. In SI units, it is equal to 4 pi times 10 to the 7. We use the right-hand rule to find the direction, so the usual method is you curl your hands in the direction of the current, and then your thumb will point in the direction of the magnetic dipole moment. In your homework, you were asked to discuss or figure out the anti-Helmholtz coil, which has two anti-aligned magnetic dipole moments. In this animation, you will see the magnetic fields move like so. In your homework, you're asked to study the magnetic field along the z-axis. So, if we go back to the previous slide, you will see that you should use the magnetic dipole moment and then find the magnetic field resulting from each individual moment, and then hopefully you can figure out what is going on from there. Next, we can figure out the magnetic field from a current. Our current task is to find out what B is. We know that charges generate E fields and currents generate the magnetic field. Since fields are perpendicular to the current, we cannot simply multiply times R as we did for Coulomb's law. We need a cross product. This will lead us to the Biot-Savart law. As you can see, it's a disgusting integral that looks a lot like Coulomb's law. We have our fundamental constant, we have a 4 pi, we have an R squared, the current instead of a charge. The difference is that it's a cross product now between the current line, the line at which the current is going under, and the direction to the point along the current that you're integrating or measuring the field from. So it is not a simple thing to compute. As such, we should figure out and try and figure out ways in which we can simplify this. And ideally, we want a symmetry. In electrostatics, we used Gauss's law, which discussed symmetry of surfaces. Let us try and figure out what symmetry we can use here to find the magnetic field. In electrostatics, a charge is distributed field lines over a surface. If you recall, field lines emanated from some point-like source called a monopole, and it distributed over a sphere. And we figured out from there that in general we could say that the electric field should be constant over spheres of symmetry, and this allowed us to find the electric field in a much simpler fashion by equating the integral of the electric field over that sphere, and then equating it to the source, which was the enclosed charge. In magnetostatics, we know that the magnetic field are lines for circles about the current. Sorry, that should say of circles. So it's a circle that comes around here, and as you can see, it's not a surface. What it generates is a one-dimensional polygon about our source. So it's slightly different. That is the first thing to notice. We're interested in 1D polygons and not 2D surfaces. Aside from that, everything else more or less carries through in the same way. We integrate the field over a perimeter of some loop that respects the symmetries of our object, and it will be proportional to the source, where the source is the enclosed current. Before going over examples, let us discuss how you actually use this law, which is called Ampere's law. The first step is to draw an Amperean loop. We draw a one-dimensional shape that respects the symmetries of the object in consideration. For example, we will often be dealing with a wire, which has cylindrical symmetry. Slicing it up, we know that the magnetic field lines move along circles via the right-hand rule, and so we can do that. Generally, the way in which I will do this is I will use the right-hand rule to figure out what the direction of the field is, and then I will try and draw a loop that moves along that direction. Then we can find the circumference of the loop. If it's a circle, it is going to be 2 pi r. Then we can find the enclosed current, either by counting the individual currents or by integrating through the current density. We will see both examples. First, let's consider the magnetic field from a wire. The wire, as you can see, is just a straight line. In our case, we're going to consider it to be infinitely small. I've given it some dimensions for the sake of clarity. The first step is to note that the field lines move in circles about the wire, so we should draw a circle. The circumference is 2 pi r. The enclosed charge is just I. It's the charge from the current. So when we plug that all in, we have B divided by this, B times the circumference, so I divide it on both sides, 2 pi r with mu naught I on top. Then I input the direction afterwards to account for the fact it's moving in a circle. Phi hat is a angular direction. That indicates that the field is moving like so, in this radial direction. Or sorry, not radial, in this angular direction. Note that the other two coordinates are going to be radial, which moves directly outwards from the center, and z, which moves directly upwards. Phi hat is the direction that moves radially. Now let's talk about a macroscopic conducting wire, as that will illustrate when you would need to integrate as opposed to just count. So here I'm drawing a cross-sectional diagram of our conducting wire. As you can see, it's solid in the center and has a uniform charge inside of it, and it's empty on the outside. Our first step is to divide the space into two regions, just like we did with Gauss's law. There is an inside region and an outside region. The inside region has its own loop and the outside region has its own loop, but because the symmetries are the same, they have the same exact loop. And since it's the same as the wire, the left-hand side is still going to be B times 2 pi r. On the right-hand side, which talks about the enclosed current, the inner loop is going to enclose some of the current, whereas the outside loop encloses all of it. So I am justified in writing this. B times 2 pi r, which accounts for the loops, is equal to mu naught times the enclosed current for r less than a, and it's mu naught times the whole current for r bigger than a. Now we need to figure out what the enclosed current is, and so we can do this calculation. The enclosed current is equal to the integral of the current density times the area. The current density is equal to the total current divided by the total area, and it is constant. Then the integral of the area gives you the area that is enclosed by this loop here. And this is just going to be pi r squared, since r is the distance to this loop. Then the pi's cancel, and I end up with an enclosed current that is the total current I times r squared over a squared. The B field outside is the same as the wire that we found before, but inside, instead, I have to use this enclosed current, and I find that some of the r's cancel, and I get 2 pi a squared on the bottom. And this would be the B field inside of this conducting wire. We can briefly talk about homework problem number 2, which is an extension off of this. Instead of just 2 regions of space, you now have an extra boundary. So as you can see, you have 2 additional regions of space. And then you will have to figure out whether you just count the currents or use the current density and figure out from Ampere's law what that is. Now that we've discussed wires, we are ready to discuss the next step in complexity, which is a more complicated geometric object that does not use a circle as its Amperian loop, the magnetic field in a solenoid. The first step is that the field lines go straight, so we want a rectangle. I've put a picture of a solenoid here, and as you can see, if the current goes this way, you can use the right-hand rule to show that the field lines on the inside should go directly through. Then, I'm going to take the solenoid to be infinitely long so that the symmetry is maintained. I don't want to take into account these fringing effects because that adds unnecessary complexity to the problem. Then, because the field lines go straight, I want an Amperian loop that has a straight edge, and that is a rectangle. The second step is that the left-hand side is B times L. B only touches one side, and because the integral had a dot product, you want the side that is parallel to the magnetic field. These three sides can be ignored. It is just B times this length L. The enclosed current is N times I, because N is the total number of turns within my loop, and I is the current through each. For example, in this problem, I have one loop here, so that's current I. This is another current I, so that's 2I. Another current 3I, so that's 3 loops, so 3 turns times I. In general, it will be N times I, since our Amperian loop is arbitrary. Then, I want to get rid of the arbitrary numbers N and L, and divide them for something that is not arbitrary but known, which is the number density little n. And this gives us the result that is stated here. B equals what should be mu naught times little n times I. I understand that this is mu. Do not get this confused with the magnetic dipole moment. This is mu naught, which is the 4 pi times 10 to the 7 constant. Homework problem number 3 also deals with a solenoid, but we're looking at an electron that is going to go in a helix. So if we want to look at this animation, here's what happens. That was a little bit quick, but you had an electron that went in, and then it went in a helix about this. So there are 2 components to this electron's velocity. One is where it moves in a circle, and the second is where it moves straight forward. The part where it moves straight forward is parallel to the magnetic field, so it is unaffected. The part that moves in a circle has a velocity that is perpendicular to the magnetic field, and therefore generates a force which is perpendicular to the velocity. We understand that whenever the force is perpendicular to the velocity, we have a centripetal force, and so it moves in a circle, thus generating a helix. So in this homework problem, you are asked to figure out how to find out what this initial velocity is. So try and figure out what is the way in which we relate 2 distinct components. We parametrize them by the same type of number, which is the time, if you recall from mechanics. And so try and figure out what the time is for each, how to relate the 2, and then you should hopefully work through the problem like so. Now let's figure out our last example, which is the magnetic field from a torus. A torus is formed by taking a solenoid and enclosing it into a donut. In a sense, I've taken 2 sides of the solenoid and brought one end to the other. Thus, I can do the same thing with my Amperian loop. Instead of having it be a straight edge, I take one end of my edge and bring it around to the other, thus forming a circle. So it is exactly the same as the solenoid, except the loop is a circle and not L, indicating that I should replace L in the formula from before by 2 pi r. Thus giving me my magnetic field, mu naught is equal to, B is equal to mu naught times the number of turns, which is now finite and countable, times the current I, divided by 2 pi r. Now I want to take a side note and discuss this a little bit further from a little bit more interesting perspective. This is a torus, which I call T2, but it's not the same as a cylinder. For example, the solenoid is not what we call closed, in the sense that it has an open edge at the bottom and it's not compact. It doesn't close in on itself. You can't, in a torus, you always have a way of getting from one end to the other and walking around in circles. So it's not exactly the same. Mathematically, we say that the torus is something that can be transformed into a plane. So since it's not the same as a cylinder, why is the form so similar? It's not the same, which in topology we call homeomorphic, but the reason is that the torus results from an identification of 2 ends of a cylinder. It forms what we call a quotient space. Mathematically, we can write it as such, but we can also think about it pretty intuitively and geometrically, so you can ignore the math and try and look at the diagram. I have 2 sides A, and I bring them together, and then I have the other 2 sides B, and I bring those together, and that forms the torus. As such, I formed a torus via the identification of multiple sides. And since I formed them via an identification, any geometry that is associated with it should undergo the same transformation. The geometry that was associated with the cylinder, i.e. the solenoid, was the Amperian loop, and I underwent the same exact identification of each of its sides to create a new Amperian loop. And from that, I could find what the magnetic field was simply by replacing what was different, L with 2 pi r. So here's how we summarize this. We understand how forces result from magnetic fields, but we need to know how to find the field. The easiest way to find the field is to use the symmetries in Ampere's law. You can set up a loop with sides parallel to the loop, so a circle to match a circle, or a rectangle to match straight lines. Find whatever the perimeter circumference is, and then find the enclosed charge and plug it into the formula. You find these enclosed charges as we did in Gauss's law for enclosed charges. You either count the number of currents or you integrate the current density. Thank you for watching this video. I hope you enjoyed it, and I will see you on Zoom next week.